There's a particular kind of silence that hums. Stand beneath the open sky on a winter night, and you can feel it, the thin, bright hush between the stars. It is not empty. It is full of stories the universe tells in frequencies our ears were never built to hear. For a century, we have learned to listen. We have tuned gigantic metal dishes to the sky, coaxed faint pulses from the hiss of cosmic noise, and trained patient algorithms to follow the ghost of a pattern across oceans of static. We have transformed mountains of silence into a science. And yet silence remains the dominant note. For every burst that spikes on our instruments, there are 1,000 more that never arrive, 1,000,000 we will never see. The cosmos is a library of light, but it is also a library in which many books never reach our reading room, pages lost to distance, time, and expansion. One question keeps returning to us like an echo we cannot stop chasing. What if somewhere out there, or sometime in the history of the cosmos, the universe sent one final, unmistakable signal, and then the lights went out? What would that signal mean? And could we ever know it for what it was? This film is not a flight of fancy. It is a journey across decades of careful observation, engineering brilliance, and sober astrophysical reasoning. We will walk the wire between wonder and rigor. Listen to the sounds real instruments have captured. Understand the physics that lets a message travel across light years, and examine the constraints that make the idea of a last signal more than just a poetic conceit. Along the way, we will meet the instruments, the phenomena, and the people who taught us the language of cosmic signals, and we will confront why the universe might one day, or already, be largely silent. Understanding cosmic signals. When astronomers speak of a signal, they do not mean an act of will by a distant mind. They mean a measurable, organized variation in some physical quantity, most commonly in electromagnetic radiation, that stands out from the background. Signal is a pattern, a spike at one exact frequency, a repeating pulse, sudden sweep across a band. It is anything that breaks the statistical sameness of what we expect from natural sources. To understand how we might detect a decisive signal from the cosmos, we must first understand the medium that carries information, the electromagnetic spectrum. Light is not just the narrow band visible to our eyes. It is a continuum that includes radio waves with wavelengths longer than a swimming pool, microwaves that warm our food, the familiar visible colors, and extremely energetic X-rays and gamma rays. All of these are manifestations of the same fundamental phenomenon, oscillating electric and magnetic fields traveling through space as photons. Different astrophysical events favor different parts of the spectrum. Cold clouds glow faintly in radio and infrared. Hot plasmas blaze in X-rays. Importantly for the search for intentional transmissions, radio waves, long, low-energy photons, are excellent carriers of information across interstellar and even intergalactic distances. They are relatively easy to produce and can pass through intervening dust and gas that would otherwise obscure optical light. But the cosmos is not a quiet channel. Every source of radiation, every star, every galaxy, every cosmic particle colliding with interstellar gas contributes to a background we call cosmic noise. Superimposed on that noise are transient events, pulsars that sweep beams like cosmic lighthouses, stellar explosions, magnetars that flare with incredible intensity, and mysterious fast radio bursts that flash and fade in milliseconds. Distinguishing an organized, possibly artificial signal from the chaotic orchestra of natural emission demands two things: sensitivity and discrimination. Sensitivity is a measure of how faint a signal our instruments can detect, a function of telescope size, receiver design, observing time, and the amount of thermal and human-made interference. Discrimination is how well we can tell whether a detected pattern is merely a natural process or something that betrays design. Scientists look for signals that are narrowband, confined to an extremely small range of frequencies, or that show deliberate modulation, repetition, or other telltale signs of encoding. Natural astrophysical processes tend to produce broadband emission, or signatures tied to known physical mechanisms Narrow band, stable, and information-rich carriers are rare in nature and therefore suspicious in the most constructive sense. How do we actually detect these signals? The modern radio observatory is both a sensor and a translator. A radio dish collects electromagnetic waves and focuses them onto a receiver where they are down-converted and digitized. Once in digital form, these voltages can be Fourier transformed, filtered, accumulated, and searched for deviations from noise. Arrays of dishes can be used in concert to synthesize a single, larger aperture, a technique called interferometry, providing tremendous resolving power. Software now sits at the heart of modern searches, machine learning systems trained to separate terrestrial radio interference from promising candidates, and pattern recognition pipelines designed to flag the most interesting events for human review. Humanity's search for signals. The story of listening is also the story of the instruments and institutions that taught us to hear. The first organized experiment explicitly aimed at detecting extraterrestrial intelligence dates to the early 1960s, when Project Ozma pointed a radio telescope at nearby sun like stars in the hope of catching a deliberate transmission. The decades that followed saw more systematic efforts. Observatories were built and dedicated time assigned to the cause. The Big Ear Radio Telescope in Ohio scanned the heavens for narrowband transmissions, while networks of radio dishes around the world were repurposed to search for technosignatures in frequencies where cosmic noise was lower and human-made interference rarer. Two institutions loom particularly large: the SETI Institute, a hub for scientific study, and initiatives like Breakthrough Listen, funded to dramatically expand the search, have together ushered in a new era. The Allen Telescope Array, for example, was built specifically to serve dual roles: traditional radio astronomy and continuous SETI observations. Breakthrough Listen invested in observing time on some of the world's most powerful radio telescopes, enabling scans of the sky with sensitivities and bandwidths previously impractical. These efforts transformed a handful of twilight hour scans into a sustained, systematic sweep of the radio sky. The modern search is not only a matter of turning dishes skyward, it is an interplay between hardware, software, and strategy. Historically, many SETI searches focused on the water hole, quiet band in the radio spectrum flanked by the emissions of hydrogen and hydroxyl, near 1.42 gigahertz. The idea was that a civilization aware of chemistry and radio might pick out that quiet window to transmit. Today, however, search strategies are far broader. We scan broad swaths of frequency space, monitor for transient bursts across millisecond to years-long timescales, and look for unusual modulation patterns that could carry information. The instruments are also changing. ROM, single dishes to phased arrays, from narrowband spectrometers to high-time resolution systems capable of catching even the shortest, brightest bursts. It is tempting to imagine that, given enough sensitivity and cleverness, we will simply catch an intentional transmission. The reality is more complicated. The sky is vast. Transmission power and directionality matter. A civilization aiming to send a beacon across the galaxy faces enormous energy costs if it wants the signal to be detectable by every world. Conversely, an omnidirectional, low-powered leakage of radio waves, like our own television and radar broadcasts, fades quickly with distance and becomes buried in the noise of 1,000 other sources. So the search balances two possibilities: targeted beacons, high power; narrow-angle transmissions intended to be noticed, and inadvertent leakage that would require us to be within a relatively short distance to detect. Mysterious signals. We have detected, yet even absent a clear, repeated handshake from another mind, the universe has given us enigmas that test the limits of our instruments and theories. These are the anomalies that drove both excitement and caution, signals so strange they forced astronomers to check, cross-check, and sometimes recheck their assumptions. The wow signal is the story every listener tells. On August 15th, 1977, a routine printout from the Big Ear Radio Telescope in Ohio produced a sequence that leapt from the paper. The intensity record showed a narrowband spike that lasted the full time the telescope could have seen it, then vanished. Jerry Emmons circled the sequence and wrote, "In the margin? Wow." The signal was compelling for several reasons: its narrow bandwidth, its strength, and its apparent origin far from any known human transmitter. For decades, the WOW signal has remained a thorn in the side of both skeptic and believer alike. Many plausible terrestrial explanations have been proposed. Others have pointed out the limitations of the dataset and the fact the signal never recurred. Its unresolved nature is an object lesson in scientific restraint, a striking event, but not a proof. In a different register, fast radio bursts, FRBs, have reshaped our understanding of the universe's transient radio sky. First discovered in the early 21st century, FRBs are millisecond duration flashes of radio energy that, in many cases, originate from extragalactic distances. Their intensity and brevity make them both spectacular and hard to study. Some FRBs are one-off events, while others repeat unpredictably. The discovery of repeating FRBs and precise localizations to host galaxies have allowed astronomers to study their environments and energetics. While most models of FRBs favor extreme astrophysical origins, such as magnetars, compact object mergers, or emission associated with young neutron stars, early on their strange properties prompted debate about artificial origins. The current scientific consensus leans strongly toward natural mechanisms, but FRBs remain an active field with surprises still emerging. Pulsars provided the first real shock when a steadily repeating, periodic radio source was discovered in 1967. Astronomers initially called them LGM, for little green men, because of their precise, clock-like pulses. Only later was the physical mechanism understood: a rapidly rotating neutron star with a misaligned magnetic field sweeping beams of radio emission across space. Pulsars are now used as tools, precision clocks for testing general relativity, probes of interstellar plasma, and, in some projects, as part of a galaxy-scale timing array to search for gravitational waves. Each of these cases reveals a central truth: the cosmos contains phenomena both regular and wildly unpredictable. The most puzzling signals have often accelerated our understanding, forcing new theories and better instruments. They also remind us that anomalies are rarely decisive. Science proceeds by accumulation of evidence, not by single, isolated events. The limits of detection. To consider a last signal, we must understand where the limits lie. Light is fast, but it is not instantaneous, spatial, throughout spin-found-diligence. The ray void Ivan can see today happened in the past, and how far in the past depends on distance. The physical universe is expanding, and that expansion stretches light to longer wavelengths, what astronomers call redshift. What astronomers call redlengths. What astronomers call red astronauts forward and cliff. One understand it. Astronomers call redshift. Estimate matic blast, redshift up. Light its files have all of it. A signal emitted as a radio wave billions of years ago will, by the time it reaches us, be shifted to lower frequencies, diluted in energy, and delayed by the travel time imposed by cosmic scales. Distance also imposes a form of attrition. Photons spread out as they travel. A narrow beam transmission will hit its target if the target is directly in its path. An omnidirectional broadcast weakens with the square of the distance. Intervening matter, interstellar and intergalactic gas, plasma turbulence, and magnetic fields scatters, disperses, and sometimes absorbs parts of the waveform. For radio signals, dispersion is particularly important. Lower frequency components travel slightly slower through ionized plasma, arriving later than higher frequencies. By measuring dispersion, astronomers can estimate how much intervening plasma a signal traversed, and conversely. Dispersion can smear a short pulse into invisibility if we do not account for it properly. There is also an ultimate observational boundary, the observable universe. Because light has a finite age, and the universe expands, there are regions beyond which signals emitted now will never reach us. And conversely, emissions from beyond a certain distance may stretch so much that their energy is practically undetectable in any feasible observation. The expanding metric of space-time creates horizons. For signals we might hope to intercept from distant civilizations, these horizons, combined with the inverse square dimming and redshift, impose strict constraints on how far a message could be intended to reach. Natural VZs. Artificial signals. One of the trickiest intellectual tasks is deciding whether a particular signal is natural or artificial. Scientists approach this with a mixture of astrophysical modeling and statistical reasoning. Natural sources often have characteristic signatures: pulsars with their regular spin-down properties, molecular masers with their spectral fingerprints, or black hole accretion disks with broad thermal spectra. Artificial signals, by contrast, might show hallmarks of engineering: an extremely narrow frequency band far from expected natural emission, structured modulation patterns inconsistent with known physics of astrophysical emitters, or repetition patterns that suggest encoding. But the line is not clean. Natural processes can sometimes mimic artificiality, and our cultural prejudices color our expectations. A narrowband spike could conceivably arise from a natural maser process under the right conditions. A repeating sequence could be the result of orbital dynamics or periodic astrophysical engines. To be confident, scientists demand multiple lines of evidence, recurrence, spatial localization, cross-validation with different instruments, and elimination of terrestrial interference. This conservatism makes discovery slow, but it guards against false positives in a field where a single mistaken claim could reverberate far beyond science: the silence of the universe. If we listen to all the sensible places and hear little that suggests a chorus of galactic civilizations, we must grapple with the Fermi paradox, the tension between the high probability estimates for habitable worlds and the apparent lack of evidence for other technological societies. There are many careful scientific resolutions to this paradox that do not invoke metaphysical gloom. Perhaps technological civilizations are rare, brief, or choose not to broadcast. Perhaps their signatures are not in the radio band, but in technologies we do not yet know to look for. Perhaps cosmic timescales mean that civilizations rarely overlap. The signals of a species that peaked a billion years ago may have passed us by long before Homo sapiens existed. Silence can also be a byproduct of physics and engineering. The energetic costs of broadcasting across interstellar distances are immense. A civilization broadcasting omnidirectionally at a strength detectable across many thousands of light years would need stupendous power or clever relay systems. Directional beacons are far more economical, but they require knowledge and intent. You must know where to point. If most civilizations are pragmatic rather than evangelistic, they may prefer to keep transmissions brief, targeted, or entirely internal. The concept of a last signal. What does it mean to speak of a last signal? The phrase implies a termination, an endpoint beyond which no further detectable information flows. In an astrophysical context, a final signal could take many forms. It could be a deliberate, intense beacon designed to reach out as an act of cosmic farewell. A civilization in terminal decline concentrating its remaining energy into a single, last message. It could be a byproduct of a cataclysmic event that releases an enormous impulse of electromagnetic energy. It could be the last coherent emission from a class of objects that will, through cosmic evolution, no longer produce signals detectable by any observer. From a physics perspective, the long-term future of the cosmos is shaped by cooling, expansion, and the slow decay or disappearance of energy gradients that drive the phenomena we observe. Stars die, galaxies grow faint, and in the very far future, entropy increases as the universe approaches states of lower free energy. In such a narrative, the number of naturally occurring, high-energy transient events will dwindle. Advanced civilizations, if any persist, will face the same thermodynamic constraints. Their ability to produce powerful signals depends on access to free energy. But a last signal does not have to be metaphysical drama. It can be a realistic projection of timescales and probabilities. Suppose a civilization in a distant galaxy, facing a dwindling energy budget, emits an enormous narrow beam transmission in the hope of contacting others. If we are in the narrow path of that beam, we would receive a message that, given the eras involved, might be the only intelligible transmission we ever intercept from that region. Conversely, if many civilizations choose to send such beacons in a cosmological epoch that is ending, a period when raw energy becomes scarce, we might live in a universe where the pace of signaling declines and, in the far future, dwindles to near silence. Humanity at the edge of time. All of this raises an existential question: why do we search? Is it vanity, curiosity, a scientific imperative, or some deeper drive to connect? The search for signals is the attempt to answer the oldest human question: are we alone? With the tools of modern science. It is also an assertion of humility. We accept that the universe is vast, and we are puny, yet we also accept that we can measure, test, and gradually understand. There is an emotional texture to the search. The act of listening across the radio dial, night after night, with enormous telescopes and elegant software, is a practice of hope. Each candidate signal is a knot of possibility that elicits the sharpest mix of skepticism and longing. To conceive of a last signal is to confront finitude. It forces us to imagine that messages can be both immortal and evanescent, immortal in principle, traveling across light years, but ephemeral in practice, stumbled upon by a single, small species at a single point in its own history. Yet the search itself matters even in the absence of a detected interlocutor. Our probes, telescopes, and algorithms expand the perimeter of human understanding. They knit us into the cosmos not by proof that another intelligence exists, but by demonstrating that meaningful information can, and does, traverse the gulf between stars. Whether or not the universe is crowded with ears, our own act of listening is the expression of a species that values evidence, connection, and the humility of asking questions that are bigger than our lives. Final act and conclusion preview of what comes next. In the next part of this documentary, we will go deeper. We will examine specific cases in detail, the instruments that have shaped the search, the science behind the most puzzling signals, and the physics that governs how a last signal could be created and received. We will visit the laboratories and observatories, where data becomes knowledge, trace the path of a photon from a distant burst to a detector, and analyze the limits imposed by cosmology and thermodynamics. We will speak with scientists whose work sits at the interface of patience and possibility, the radio engineers, the data scientists, the theorists, and we will consider whether there are practical strategies humanity can employ to increase the chances of intercepting a truly consequential message. For now, end this part with a single image, the radio dish, enormous and patient, turning slowly toward the sweep of the Milky Way. It listens, not because it expects certainty, but because listening is what we do. The cosmos hums with processes we are only beginning to understand. Somewhere within that hum there may have been, or may one day be, a signal that changes everything, whether it arrives as a deliberate beacon, a last mechanical heartbeat, or a natural flash that we interpret as meaning. The work of listening is the work of bearing witness. As the silence of space stretches out before us, humanity has built ever more impressive ears to listen, giant telescopes that act as our proxies, straining to catch the faintest whispers from the stars. In the Appalachian Hills of West Virginia, for example, the Robert C. Byrd Green Bank Telescope stands like a vast steel dish, 100 meters wide, its unblocked design ensuring that every photon counts. This instrument can pivot to point almost anywhere above the horizon. It covers a sprawling range of radio frequencies and is so sensitive that it can detect whispers from distant pulsars and even the faint signals of our own spacecraft at the edge of the solar system. The Green Bank site is a designated radio quiet zone, with no cell phones or Wi-Fi allowed for miles, so the telescope hears nothing of our earthly chatter. Its cold receivers some cooled to just 15 Kelvin. Keep the telescope's own noise extremely low. Green Bank astronomers use it daily. They time pulsars to nanosecond precision, map hydrogen gas in galaxies billions of light years away, and even support interplanetary missions. In 2017, GBT picked up transmissions from New Horizons near Pluto. During SETI observations, Breakthrough Listen pours millions of dollars into instruments on Green Bank, scouring every beam for patterns that might betray intelligence. Engineers constantly tweak and upgrade the telescope, polishing panels and adjusting electronics at any moment. Teams of scientists stand ready to receive anything that might slip through the cosmic static. In contrast, Arecibo Observatory in Puerto Rico offered a different design. There, engineers carved a 305-meter diameter dish into a natural sinkhole, a gigantic reflector that for over 50 years was humanity's most powerful radio eye. Instead of moving that vast mirror, they built a 900-ton platform 150 meters above it, from which receivers could be steered to scan about 20 degrees of sky around the zenith. Arecibo's collecting area was so immense that it could detect exceedingly weak signals. It played a leading role in multiple breakthroughs. It discovered the first pulsar, orbiting another neutron star, earning a Nobel Prize, precisely mapped asteroids with radar, and even detected the first planet around a pulsar. In fast transient astronomy, Arecibo caught a bright millisecond burst that would later be called FRB 1211102. That one burst was puzzling at first, but the key came later when more pulses arrived from the same spot. Sadly, in late 2020, the observatory's cables snapped and the dish collapsed, ending its 57-year run. Yet its scientific legacy lives on. The next generation giant dish, China's fast 500-meter aperture spherical telescope, has taken up the mantle. FAST's reflector spans 500 meters, though at any time a 300-meter segment is actively focused by 4,500 individually tilting panels. Its suspended receiver cabin moves on cables to catch the waves. Fully operational since 2020, FAST now pushes the sensitivity frontier. It has already discovered dozens of new pulsars, and even recorded radio bursts from a magnetar in our own galaxy, showing that its vast ear can catch whispers even from the nearest stars. FAST exemplifies how far our engineering has come, carving a bowl out of the Earth and filling it with the world's largest steerable radio dish. But equally important are telescopes that use many smaller pieces. In California's Hat Creek Valley stands the Allen Telescope Array ATA, a facility built from the ground up for the search for extraterrestrial intelligence. It has 42 dishes, each only 6 meters across, tiny compared to Arecibo or FAST. But through clever digital electronics, they operate as one coherent instrument. Covering roughly 1 to 14 gigahertz, the ATA's signals are combined so that dozens of independent beams can be formed at once. In effect, ATA can watch many parts of the sky simultaneously. Its entire mission time can be devoted to scanning the heavens for unusual transmissions. ATA's philosophy is that SETI should be a steady vigil, not a sporadic glance. Students and researchers run scripts each night, pointing at nearby stars, exotic targets, and known exoplanet systems, hoping to catch anything narrowband or patterned. If a candidate turns up, they can immediately point the whole array at it for confirmation. While ATA hasn't yet found a clear extraterrestrial beacon, it has done plenty of general astronomy, mapping hydrogen in the galaxy, studying pulsars, and even participating in planetary radar studies. Its pioneering work has shown that an array of many small dishes can be dedicated full-time to SETI, inspiring plans for future arrays that will cover even more sky with higher sensitivity. Across the globe in the southern hemisphere, another array is making waves. South Africa's Meerkat consists of 64 dishes of 13.5 meters each, spread over 8 kilometers in the quiet Karoo Desert. Completed in 2018 as a precursor to the massive square-kilometer array SKA, Meerkat immediately became one of the world's most sensitive telescopes. by linking its 64 antennas through interferometry, Meerkat achieves both enormous sensitivity thanks to its total collecting area and razor-sharp resolution thanks to its long baselines. It is essentially a single telescope 8 kilometers across. Early science with Meerkat has been spectacular. It has mapped the distribution of hydrogen gas in distant galaxies, discovered dozens of new pulsars, and even imaged mysterious odd radio circles in deep sky surveys. Crucially for fast transients, Meerkat's real-time pulsar/backend system called Meertrap has caught FRBs in action, even performing immediate follow-up observations to refine their positions. South African astronomers say Meerkat can survey the sky about 10 times faster than any single dish in the Southern Hemisphere. In its Cape Town Control Center, teams of scientists monitor Meerkat's output continuously. One astronomer joked that Meerkat is like having 10 Arecibo's in one because of its collective power. It sets the stage for SKA, and indeed Meerkat will remain operational, laying the groundwork for the even greater sensitivity to come. Far to the north, European scientists built the low-frequency array LOFAR, and it looks nothing like a traditional telescope. LOFAR spans multiple countries with nearly 20,000 simple dipole antennas, mostly in the Netherlands and Germany with stations across Europe. Each LOFAR station digitizes its antenna signals and sends them via high-speed links to a central supercomputer. By precisely timing and combining the data from stations separated by hundreds or even thousands of kilometers, LOFAR effectively forms a radio telescope of continent-wide size at low frequencies. Because LOFAR works in the tens to a few hundred mHz range, it can probe phenomena that glow brightly at those long wavelengths. For example, cosmic rays striking Earth's atmosphere emit a radio flash that LOFAR can image in unprecedented detail, and the diffuse glow of the early universe's neutral hydrogen, never directly seen before, is within reach. LOFAR's angular resolution can be extremely fine, fractions of an arcsecond, when using the most distant stations. It has already discovered many new pulsars, including the first radio pulsar in the Andromeda Galaxy, studied solar flares and Jupiter's magnetosphere, and even monitored the entire sky for transients. Because it has no moving parts, LOFAR can retune its beams and software on the fly, essentially acting as thousands of small telescopes all pointed by clockwork. One challenge is that at such low frequencies, the ionosphere and human-made radio can swamp the sky. LOFAR engineers solved this by adaptive filtering, noticing when an airplane or lightning was in view and blanking it out. Today, LOFAR is a model for SKA's low-frequency component, proving that a 4 telescope with simple antennas can be as mighty as a dish thousands of kilometers across. Another innovative instrument is CHIME, the Canadian Hydrogen Intensity Mapping Experiment. CHIME's hardware consists of 4 fixed, north-south cylindrical reflectors, each 100 by 20 meters, lying flat on a hillside in British Columbia. It has no moving parts. Instead, CHIME watches the sky overhead continuously at 400 to 800 megahertz by forming hundreds of digital beams each second. The magic is in its computing. CHIME has 2048 analog receptors running into a supercomputer of GPUs and FPGAs that perform fast Fourier transforms and pulse searches in real time. Although CHIME was originally built to map hydrogen for cosmology, it turned out to be a fast radio burst machine. Since 2018, CHIME has detected hundreds of FRBs, more than all other telescopes combined. It has even found many new repeating FRBs. CHIME scientists issue rapid alerts for each burst, allowing X-ray and optical telescopes to follow up within minutes. One crowning moment was in April 2020, when CHIME and the small U.S. instrument STARE-2 simultaneously recorded a very bright millisecond burst from a known magnetar in our galaxy SGR 1935 plus 2154. That burst, coincident with X-ray flares seen by NASA and ESA satellites, was essentially a galactic FRB and confirmed that magnetars can indeed produce these millisecond blasts. CHIME's success has shown the power of modern digital arrays. By combining dedicated hardware with clever software, it scans the sky every day and keeps our net wide for finding the unexpected. Together, these telescopes illustrate the core techniques of radio astronomy. Sensitivity depends on collecting area and system noise. More and bigger antennas mean fainter whispers can be heard. Resolution comes from aperture. A larger dish or a longer interferometer baseline sees finer detail. By correlating every pair of antennas in an array, we synthesize a virtual dish, as wide as the array itself. For example, when the very large array's dishes are spread over 36 kilometers, it achieves detail that would require a single 36 kilometers dish. Beamforming and phased arrays allow electronic steering by adding tiny time delays to each antenna signal. An array can form a sharp beam pointing to any direction, and even multiple beams at once. This multiplies sky coverage, crucial for transient surveys. Each telescope also has a particular frequency range where its receivers work best. Some focus on the water hole around 1 to 2 gigahertz, where hydrogen's 1.42 gigahertz line sits in a quiet part of the spectrum, hoping any civilization would broadcast where natural noise is low. Others, like LOFAR or CHIME, cover lower frequencies. By spanning from tens of MHz up to 10 gigahertz, we ensure we're listening across the cosmic dial. Many signals we seek could arrive at any frequency, and only by covering the full band can we be sure not to miss them. But even as our instruments listen, the universe itself scrambles what they hear. Space is not truly empty. It is filled with ionized gas, plasma, and magnetic fields. When a radio wave travels through a plasma, its speed depends on frequency. Higher frequency, shorter wavelength waves get through slightly faster than lower frequency ones. The result is dispersion. A short pulse emitted all at once will arrive spread out in time at Earth. In practice, a radio flash might be milliseconds wide at the source, but becomes seconds long across a wide band by the time we get it. Fortunately, this effect is predictable. By measuring how much the pulse is delayed at different frequencies, astronomers can compute the dispersion measure DM, effectively the column of free electrons along the line of sight. A very high DM indicates a very long path through cosmic plasma. Indeed, the first FRBs were identified as such because their DMs were much larger than what our Milky Way could contribute, a clear sign that they came from distant galaxies. Along with dispersion, turbulent plasma causes scattering. Imagine a pulse encountering many tiny lensing clumps of plasma. The pulse will take multiple paths, some longer than others, arriving as echoes. Observationally, this shows up as a characteristic tail or broadening of the pulse. At the lowest frequencies, LOFAR band, scattering in our own galaxy can completely wash out a short pulse. At G's frequencies, it's usually milder but still measurable. Some FRBs show an exponential decay on their trailing edge, evidence of scattering either in their host galaxy or along the way. Scientists often try to just scatter pulses in software or simply avoid frequencies where scattering dominates. Either way, understanding scattering tells us about the interstellar medium itself and helps us recover the original signal's sharpness. Motion also affects the received signal. Both the Earth and any distant source have velocities, so a fixed frequency transmission would be Doppler shifted. In Radio SETI, analysts expect a beacon to drift in frequency due to the source's rotation or orbit. For example, a transmitter on a planet like Proxima b would have a sinusoidal daily drift as it rotates. Similarly, Earth's own rotation and orbit cause signals to drift by a few spur-second, in a predictable way roughly 1 KIGs over a day at 1 GHz. SETI pipelines correct for these effects. A signal whose drift pattern doesn't match any plausible celestial motion is likely terrestrial interference. This was a key clue in the Proxima Centauri candidate. Its frequency drift did not match a real star signal once all motions were accounted for. In practice, technicians compute and remove Earth motion Doppler from the data when searching. On the grandest scale, cosmic expansion stretches all wavelengths by a factor 1 plus z, where z is redshift. A flash emitted at 2 gigahertz in a galaxy with z equals sign 0.5 would arrive here at approximately 1.33 gigahertz. Time intervals stretched by the same factor, a 1 ms burst, there would appear 1.5 ms here. When FRBs can be localized to host galaxies, astronomers take spectra of the host to measure z. Then they can say exactly what frequency and duration the burst had when emitted. For example, pinning down FRB1, 2, 1. 1, 0, 2's dwarf host at z equals sign 0.1, 9. 3 allowed astronomers to calculate that the bursts were even more energetic and shorter in their own frame than they appeared. Armed with all this knowledge, astronomers have unraveled many candidate signals. The first FRB, detected by Lorimer's group, had astronomers across the field scratching their heads. That single, brilliant 5 ms pulse had a DM beyond the Milky Way's expected contribution. Lorimer's team went to great lengths to prove it wasn't a glitch. They checked for any local interference sources, replayed the data with the dish offset, and did every test imaginable. In the end, they published it, describing it as an exceedingly bright flash of unknown origin. They had been dreaming of such an event at least as a possibility. And when it finally appeared in archival data, they could hardly believe it. Afterwards, they found dozens more pulses in the same data, each lending confidence. By 2013, Parkes astronomers published additional FRBs from acted in one survey. They saw 4 more bursts, each with high DMs confirming an extragalactic origin. Around the same time, Green Bank and Arecibo also reported new FRBs at different frequencies. It became clear that these bursts weren't one-offs, but a new class of cosmic events, happening in the sky all the time, perhaps thousands per day across the game, truly changed when an FRB was found to repeat. In 2012, FRB 1, 2, 1. 1, 0. 2 appeared once at Arecibo, but when a dedicated team led by Laura Spittler-Ree observed the spot in 2015, dozens more bursts arrived from exactly the same coordinates. The excitement was palpable. Astronomers quickly trained every available telescope on that location. Months passed until finally, in 2016, the Very Large Array and other interferometers recorded simultaneous bursts and pinned down the position to millirexicon precision. That localization pointed to a tiny star-forming dwarf galaxy about 3 billion light-years away, and even revealed a steady radio source at the same spot. Suddenly, FRBs were real astrophysical objects we could study in detail, not just curiosities. The fact that FRB 1, 2, 1, 1, 0, 2 repeated meant it could not have been a one-time cataclysm like a neutron-star collision. It must be a persistent source, maybe a young neutron star or magnetar in a nebula. In the end, they published it, describing it as an exceedingly bright flash of unknown origin. They had been dreaming of such an event at least as a possibility, and when it finally appeared in archival data, they could hardly believe it. Afterwards, they found dozens more pulses in the same data, each lending confidence. By 2013, Parkes astronomers published additional FRBs from active surveys. In one survey, they saw 4 more bursts, each with high DMs, confirming an extragalactic origin. Around the same time, Green Bank and Arecibo also reported new FRBs at different frequencies. It became clear that these bursts weren't one-offs, but a new class of cosmic events, happening in the sky all the time, perhaps thousands per day across the sky. The game truly changed when an FRB was found to repeat. In 2012, FRB 1, 2, 1. 1, 0, 2 appeared once at Arecibo, but when a dedicated team led by Laura Spittler-Ree observed the spot in 2015, dozens more bursts arrived from exactly the same coordinates. The excitement was palpable. Astronomers quickly trained every available telescope on that location. Months passed until finally, in 2016, the Very Large Array and other interferometers recorded simultaneous bursts and pinned down the position to millisecond precision. That localization pointed to a tiny star-forming dwarf galaxy about 3 billion light-years away, and even revealed a steady radio source at the same spot. Suddenly, FRBs were real astrophysical objects we could study in detail, not just curiosities. The fact that FRB1, 2-1, 1, 0, 2 repeated meant it could not have been a one-time cataclysm like a neutron star collision. It must be a persistent source, maybe a young neutron star or magnetar in a nebula. Not all intriguing signals have panned out, but they have taught us valuable lessons. The famous WOW signal from 1977 still lingers in lore. For 72 seconds, Ohio's Big Ear telescope recorded a narrowband spike at 1,420 megahertz, so perfect that Jerry Emmon wrote "wow" on the printout. Everyone hoped maybe a long-lost extraterrestrial beacon. But the thrill faded when no one ever saw it again. No consistent source was found despite decades of follow-up. A variety of hypotheses were suggested, even a magnetar flare lighting a hydrogen cloud, but none fits neatly. The WOW signal reminds us how one good candidate must be tested until no normal explanation remains. Modern SETI efforts have had their share of near misses too. In late 2020, the Breakthrough Listen team made headlines with a candidate signal from Proxima Centauri, our nearest stellar neighbor. Parkes had recorded a narrow spike at 982 megahertz during several observations. The team noted it was present only when pointing at Proxima, not in off-target scans, and it had a curious frequency drift. They cautiously labeled it BLC 1-inch Breakthrough Listen Candidate 1 and began a careful analysis. For a time, it felt like a real possibility. Yet, methodically, the scientists re-examined every aspect: clock offsets, known satellites, hardware tests. Eventually, they found that the signal's behavior matched known forms of terrestrial interference in digital electronics. In October 2021, they published a thorough paper concluding it was not of extraterrestrial origin. Though the media had buzzed about an alien radio station, the scientists themselves had been cautious, using terms like signal of interest instead of jumping to conclusions. This episode was a triumph of process. Data was shared, independent teams checked it, and false hope was turned into an instructive result. Behind all these searches are the people who listen. Astronomers often describe their work with equal parts wonder and humility. Dr. Duncan Lorimer said discovering that first FRB felt like stumbling onto something magical, but he also said he was uneasy, as if it could all be a mistake. When his student David Narkovic first saw the pulse, they literally held their breath until they knew it was real. Dr. Laura Spittler recalls the moment, FRB1, 2-1, 1-0-2, repeated as electrifying. The realization came in the middle of the night, and they quickly scrambled to alert other telescopes. SCT pioneer Dr. Jill Tarter has famously counseled optimism tempered by rigor. Even after decades of silence, each new day of listening may be the one that brings an answer, she says. Breakthrough Listen's chief scientist Dan Wertheimer jokes that SCT is a negative science because it usually reports nothing, yet he also notes each null result is data in itself, constraining what kind of civilizations might be out there. The human side comes through in observatories too. Imagine the control room at Parkes one night. A student sips cold coffee, watching the waterfall display tick by. Suddenly, a bright, slanted line appears across the spectrum. The student gasps, "Did you see that?" Telescopes provide instant waterfall plots, and every eye trained on them can spot an FRB. Phones start pinging quietly as colleagues wake to see. Engineers might come in to check if any local devices, even the building's air conditioner, could emit at that moment. Similar scenes happen worldwide at Green Bank. An operator might run a quick calibration scan after a candidate at Meerkat's Cape Town Center. The team discusses whether the pulse falls outside any known interference masks. Sometimes a burst survives all checks and is confirmed. Those are moments of joy. More often, the candidate fades upon closer inspection. An airplane was overhead, or a satellite transmitted in that band. But the routine of checking teaches researchers humility. Nothing is announced before it's airtight. This commitment extends to peer review. A new FRB or SETI result is presented at conferences and then submitted to journals, where dozens of scientists critique every detail. Collaborative papers emerge, often hundreds of authors, and many observatories, because modern astrophysics is a team effort. For example, the localization of FRB1, 2, 1, 0, 2 required coordinated observations by radio and optical facilities across continents. The discovery papers had authors from NRAO, Arecibo, ESO, and many universities all working together. And so, even with no confirmed ETI signal yet, our world is richer for the search. We've learned so much: how the Milky Way's electrons are distributed, how magnetars behave, even how many missing baryons float between galaxies. FRBs helped find those too. We've built machines and algorithms far more capable than once thought possible. The scientists working on SETI and FRBs share a quiet hope. They know the odds of hearing an actual alien message tonight are slim, but they believe any night could bring a surprise. They also know that every tone and pulse they catalog adds to humanity's knowledge, one way or another. As this chapter comes to a close, picture the night sky over the great observatories. Under the band of the Milky Way, radio dishes turn steadily. At Green Bank, the dome is illuminated by monitors showing live data. In the Karoo, meerkats' antennas stand gleaming under southern stars. At Chime in Canada, the cylindrical scopes stretch into the distance against the twilight. Researchers behind their consoles exchange quiet words, eyes fixed on screens of spectrograms and candidates. Graduate students code late into the night, training machine learning routines to spot patterns a human might miss. And through it all, in these quiet control rooms, there is a sense of vigil, as if these massive instruments are set as sentinels, forever listening. Hope is what binds them. Many have waited years without a breakthrough, but they maintain patience. They often say that finding an ETI signal would be like hearing a whisper through a storm. Very unlikely, but immensely important if it happens. Until then, they are grateful for every truth they extract from the noise. Each calibration run, each blank result, refines the search. Because if the universe ever does send a final message to humanity, these will be the ears ready to receive it. The last signal we might ever get could be buried quietly in vast data sets, but we will recognize it because we have trained our instruments and ourselves to listen. And even if it never comes, our journey has given us new knowledge and new perspective. We will have built monuments of steel and code to listen to the cosmos, and we will have listened in calm confidence, with patient hearts and unwavering curiosity. Thus we watch and wait beneath this silent sky, instruments ready and hearts patient, ever listening for that next elusive whisper from the cosmos. The moment a mysterious blip appears on a radio telescope screen, a hush falls over the observatory. In that instant, every astrophysicist and engineer becomes a detective. They know that nature can create astonishingly strange signals, and that even more remarkable patterns could, in theory, come from intelligent beings. To tell them apart, scientists must examine every nuance of the signal's shape and behavior. A key principle is that natural sources usually produce broad spectrum, chaotic emissions, while artificial transmitters would tend to be narrow, precise, and patterned. For example, the pulsar discovered in 1967, the first of its kind, was pulsing with metronomic precision every 1.3 seconds. Jocelyn Bell Burnell described how it flickered every 1.3 seconds, repeating for days on end, a stark contrast to the random cacophony of most cosmic noise. Moreover, it was observed at a very specific radio frequency rather than smeared across a band of frequencies. These traits, a clean, unvarying tone and a steady pulse, conflicted with the generally chaotic nature of most cosmic phenomena, compelling the discoverers to wonder aloud if it might be a message from little green men. In fact, they playfully dubbed the source LGM-1 for Little Green Men 1. Only when a second identical pulse was found elsewhere in the sky did they realize the signal was not engineered at all, but a new kind of star, a spinning neutron star we now call a pulsar. This tale of the first pulsar sets the tone. Regularity, narrowband purity, and repetition are hallmarks of technosignatures. and anything mimicking those is examined with both excitement and skepticism. Modern SETI programs use those criteria deliberately. Instruments like the Allen telescope array scan millions of frequencies, hunting for an extremely narrow-band signal, often only a few hertz wide, because no known natural process emits something so pure and monochromatic. Our galaxy's radio sources usually have a jumble of frequencies, Dopplers shifted by gas motions or supernova turbulence, spreading the energy across a range. A signal that stands out as a single fixed tone, or that carries an obvious modulation or repeating on-off pattern, or a succession of pulses with a meaningful interval, instantly sets off alarms. Beyond raw frequency, researchers also look at polarization and dispersion. Light and radio waves from space often become polarized. One orientation of the field is favored by intervening magnetic fields, and waves traveling through interstellar plasma are dispersed, so that lower frequencies arrive slightly later than higher ones. A true cosmic flash, like a fast radio burst, will sweep downward in frequency over time, an imprint of passing through millions of light years of ionized gas. An artificial transmitter, by contrast, might have a constant frequency sweep or none at all. In practice, investigators check whether a mysterious pulse shows the telltale dispersion curve of an astrophysical source. If it doesn't, that suggests a local origin or at least a non-cosmic path. For example, the famous fast radio bursts all have huge dispersion measures, far beyond what the Milky Way could produce, firmly marking them as extragalactic. Similarly, the modulation of a signal is scrutinized. Random static has no pattern, but an artificial beacon might carry information encoded in spikes, pulses, or narrow lines. Sophisticated algorithms seek out non-random, information-rich patterns, such as sequences of prime-numbered pulses, or the specific structure of a human-made digital signal. Any hint of such order raises both hope and caution. All these features, narrow bandwidth, strict periodicity, clean polarization, are the tools scientists use to flag potentially artificial signals. The SETI Institute explicitly tunes its hardware to these criteria. At Hat Creek Observatory, the Allen telescope array continuously scans the sky for signals only a few hertz wide, while powerful processors search for anomalies that cannot be explained by natural astrophysical sources or human-made interference. Another project, Laser SETI, watches the optical sky for ultra-short flashes so intense they could only be created by clever lasers, a phenomenon with no known natural origin. In all cases, the working assumption is that nature's signals are broad and messy, whereas an engineered technosignature would stand out by its precision. Thus, any unusual signal, especially if it shows a narrow spectral spike or a clean clock like beat, triggers immediate further scrutiny. Of course, this approach has its pitfalls. The universe has a way of surprising us with natural phenomena that mimic the artificial, and our own technology can create signals that mimic the cosmic. History is full of cautionary tales. After the pulsar discovery, astronomers realized the first pulses were just fast-spinning neutron stars, but the brief wonder of aliens spoke to the seductive power of a clean signal. In the 1990s and 2000s, radio astronomers chasing fast radio bursts, FRBs, were repeatedly tripped up by peritons, mysterious G's frequency pulses detected at the Parkes telescope. These peritons showed exactly the downsweep of frequency one expects from a distant burst. Their signal descended from high to low frequency in the space of milliseconds, and they appeared in multiple beams of the multi-receiver array. At first glance, they looked just like genuine FRBs. Yet researchers noticed a critical clue. These pulses appeared in all 13 beams of the Parkes dish at once, implying they came from right above the telescope, not from space. The culprit turned out to be incredibly mundane, someone opening a microwaved mug before it had finished. The spinning magnetron in the oven emitted a swept frequency burst that perfectly mimicked an FRB until it was traced and stopped. This episode taught SET scientists a painful lesson. Even a signal that checks all the boxes for extraterrestrial intelligence can turn out to be our own kitchen appliances, It underscored the need for rigorous cross-checks and multiple lines of evidence. Likewise, signals from passing spacecraft or satellites sometimes masquerade as cosmic phenomena. In 1997, the famous WOW signal blasted the Ohio State Big Ear telescope with a narrowband tone that seemed almost hand-carved in the spectrum. But it appeared only once, disappeared, and despite decades of looking, never appeared again. Without a repeat or additional confirmation, astronomers still consider it unconfirmed, possibly a comet, or some unknown reflection, but almost certainly not a deliberate alien transmission. The principle remains: a genuine technosignature must survive exhaustive vetting. That vetting involves statistics and follow-up. Telescopes set thresholds to weed out random noise. For instance, a detection must be, say, 5 times stronger than the background fluctuations to be taken seriously. Single events are treated skeptically. True discoveries usually require multiple observations. For example, when the Breakthrough Listen team detected a signal near Proxima Centauri in 2019, they were thrilled. A line only a few hertz wide, drifting at a rate expected of an off-Earth transmitter. The signal persisted across hours and only appeared when pointing at Proxima, vanishing from control observations. Exactly what a nearby ETI broadcast might do. By all the simple rules of thumb, it was perfect. But the scientists didn't announce first contact. They set up a framework of checks, cross-observing with different telescopes, analyzing the signal structure in detail, and most crucially, asking whether anything in the equipment or environment could produce the effect. In the end, the Proxima signal, called BLC1, failed those tests. It turned out to be an interplay of local radio interference, probably a harmonic beat from the observatory's own electronics, that mimicked an ideal beacon. In fact, they found dozens of similar interference patterns in their data, revealing how commonplace such false alarms can be. The report was released with the headline, "We found something that looked almost exactly like an alien signal, and then we realized it wasn't." A testament to the thorough skepticism that guides this field. This cautious attitude is not about dosing hope, but about science. The astronomer Carl Sagan famously said that extraordinary claims require extraordinary evidence. In practice, that means every potential signal is assumed innocent until proven guilty of being alien. The default explanation is always terrestrial interference or a known astrophysical source until ruled out. It is common practice to demand independent confirmation. If one observatory sees something unusual, others aim their telescopes at the same spot in space. If the second site doesn't see the signal, it was probably local interference. SETI teams also check satellite databases, military radar schedules, even solar flare activity, because any of these can generate spurious blips. Many research projects now run off-on-off, switching. They stare at the target, then at a blank patch, then back, to see if a signal is locked to the sky or to our own instruments. Only signals that are persistent, repeatable, and telescope-independent survive this gauntlet of scrutiny. In short, scientists hold the analysis in a crucible of doubt. They comb through raw data looking for the fingerprints of life, but they simultaneously look for fingerprints of their own human technology. Project engineers install RFI monitors at observatories, record the exact performance of each receiver, and use algorithms to flag any candidate that matches known interference patterns. For example, many radio systems use clock oscillators, and their harmonics can bleed into the band. The team that studied BLC 1-inch even found interference lines tied to common clock frequencies. All of these cross-checks reflect the deep principle of scientific skepticism. To prevent self-deception, the researchers assume their discovery is wrong until they can show it is right. This discipline has paid off countless times, turning apparent marvels into mundane explanations, and ensuring that if one day a truly alien signal emerges, it will be undeniably real. Yet, for all this caution, the search continues in earnest because the question is so profound. And as the experiments grow ever more sensitive, physicists are forced to confront a sobering truth. even if a civilization is out there broadcasting. The universe imposes fundamental limits on who can hear it. These cosmic boundaries are written in the laws of physics. The fastest any signal can travel is the speed of light. In our expanding universe, that speed limit means that some regions are already receding from us faster than light can catch up. As NASA explains, space itself is expanding so rapidly between us and faraway galaxies that we are completely cut off from these regions of space-time. Those galaxies lie beyond our cosmic horizon forever. Their signals, no matter how powerful, will never reach Earth. This expansion is accelerating due to dark energy, which means even some galaxies that are visible to us now will eventually slip away past the point of no return. In practical terms, there is a finite volume of the cosmos from which a signal could even arrive, and that volume is shrinking with time. Moreover, not all places within our horizon are hospitable to light-speed messaging. Any signal weakens with distance squared, and interstellar and intergalactic media can absorb or scatter it. A radio burst from 1,000 galaxies away might arrive with only a few photons per square kilometer, easily lost in the cosmic static. Observationally, each telescope has a sensitivity threshold, a minimum detectable flux. If a civilization is too far, too small, or simply not transmitting very brightly in our direction, we will never see them. Even if we assume a powerful beacon is aimed our way, the signal still has to pierce through the cosmic noise. The universe's own microwave background, at approximately W.7 K, and the glow of synchrotron radiation from electrons spiraling in magnetic fields provide a floor of noise that a faint alien signal must outshine. Finally, cosmic time itself is not on our side. Our universe is not static. It is moving inexorably toward greater entropy. According to thermodynamics, eventually the stars will burn out, black holes will evaporate, and all that will be left is a dilute gas of photons and elementary particles at nearly uniform temperature. In this heat death scenario, there will be no processes to sustain complexity or communication. The heat death hypothesis posits that the universe will approach a state of no thermodynamic free energy and, having reached maximum entropy, will continue expanding forever. In such a cold, dilute future, even the most ingenious transmitter could not send or even generate a signal. All machinery would fail without energy gradients. Any message we receive in that distant future would be the last gasp of the cosmos' youth. In other words, there is an ultimate silence awaiting. The expansion of space carries regions eternally beyond reach, and the second law of thermodynamics guarantees an endpoint where no useful information can be exchanged. If an alien civilization somewhere out there broadcasts a final goodbye, it would have to contend with these unyielding limits. Whether through entropy or horizons, the cosmos seems to be setting an expiration date on interstellar communication. Against this profound backdrop, our search takes on even more poignancy. Each candidate's signal must survive the rigor of science, and even then, it might be caught in the final light of a fading universe. As we steel ourselves for this difficult work, we remember that skepticism is our guiding star. We will not mistake a flicker for a fire, but we will not stop listening. Because far out in the quiet sky, amid the steady hum of galactic radio noise, there may yet lie a whisper from the stars. Perhaps the last signal humanity may ever receive, echoing across the cosmic void. The universe is a vast, echoing chamber. And we have been listening. For decades, humanity has turned radio dishes and optical telescopes toward the cosmos, straining to hear any hint of life beyond our world. Yet out there in the deep night, a profound silence answers us. In this final chapter, we ask what that silence truly means. What is the ultimate fate of the cosmos? And what, if anything, will be the last signal ever sent or received in the universe? Space is not static. Thanks to a mysterious dark energy, the fabric of space-time is stretching ever faster. Galaxies are not coasting gently, they're rapidly accelerating away from one another. In time, this expansion will carry almost every galaxy beyond our reach. Only the islands of galaxies held tightly by gravity, like the Milky Way, and its neighboring galaxies will remain together. The rest will vanish into an expanding darkness. Imagine our night sky 100 billion years hence. No Andromeda, no vast clusters of stars, only the stars bound in our own little cosmic neighborhood. Everything else will have slipped beyond an invisible horizon of space. Even light can't catch up once the expansion outpaces it. The universe steadily segregates into isolated pockets, each heading toward its own lonely fate. Within these last bastions, the drama of star life continues, but it too will fade. Right now, new stars still ignite from clouds of gas and dust. For billions of years, our galaxy has sparkled with star birth and stellar death. But that era is numbered. Over the next trillion years or so, the raw material for making stars, cold hydrogen and helium, will dwindle. Star-forming clouds will all be consumed or ejected into space. Picture once majestic galaxies slowly dimming as their star factories run dry. The Stellariferous era, the time of shining stars, will end. Stars will keep burning for much longer, but no new stars will light up to take their place. Eventually, after roughly 1,0 circumflex 1,4, 1,0 circumflex 1,5 years, that's 100 trillion to a quadrillion years, stellar nurseries go dark, and the universe has no more newborn suns. Even so, the cosmos will still host light. The smallest stars, the humble red dwarfs, burn their fuel so frugally that they can shine for 1 trillion times longer than our sun will. A typical red dwarf only uses a tiny fraction of its hydrogen at a time, so it can linger for tens of trillions of years. These little stars, including even those born later from rare collisions of brown dwarfs, will far outlast any sun-like stars. In the endgame, they'll be the dominant lights in our galaxy. One could imagine a future civilization stranded in the Milky Way, living among red dwarfs long after giant stars have died. But even these will not last forever. As the eons pass, every star eventually exhausts its nuclear fuel. Massive stars explode in supernovae and leave behind black holes or neutron stars. Sun-like stars swell into red giants and then shrug off their outer layers, leaving behind white dwarfs, Earth-sized cinders made mostly of carbon and oxygen. Slowly, white dwarfs cool. Right now, they still glow white-hot, but over trillions of years, they radiate away their heat and dim. In a few more trillion years, our galaxy's white dwarfs will be near the temperature of liquid helium. They essentially freeze into black dwarfs, cold, inert stellar corpses, so dim they no longer emit visible light. Neutron stars and black holes will go on quietly in the background, but they too carry only remnant warmth from past events. Gradually, even these relics cool toward nothing. One might think the universe simply fades away to nothing after that. But there are whispers in theory of one last cosmic spectacle, a final firework. Some physicists have calculated that certain very old, massive white dwarfs, now effectively black dwarfs, could undergo a last gasp of nuclear fusion. Over unimaginable timescales, quantum tunneling might allow carbon in their cores to fuse into heavier elements. The result would be a collapse and detonation akin to a supernova. In other words, a black dwarf could explode anew. Remarkably, the first such event might not occur until about 1,0 circumflex 1,100 years from now. That's a 1 followed by 1,100 zeros of years, a span so colossal it defies human intuition. Even more surreal, the last black dwarf supernova might not happen until on the order of 1,0 circumflex 3,2. 0, 0, 0 zeros have passed. If these predictions hold, these phantom supernovae would be the universe's final grand explosions, blazing briefly in the void before, leaving behind only more black holes. In a vast emptiness, these would be the final fireworks. But after them, the lights truly go out. Other theories suggest an alternate route to oblivion. 2025 study proposed that not only black holes, but any massive object can evaporate by generalized Hawking-like process. According to this idea, even a mere white dwarf gradually creates particle-antiparticle pairs from its own gravity field, slowly bleeding away mass. Amazingly, this calculation suggests that a white dwarf might wholly vanish in about 1.0 circumflex 7-8 years, far sooner than 1.0 circumflex 1100. If so, the final end could come much earlier by cosmic standards, though still unimaginably late. In short, physics says that no matter what form matter takes, it won't endure forever. Bound states will eventually break apart, whether the clock reads 1.0 circumflex 7-8 or 1.0 circumflex 1100 years. Every last star remnant will be gone. Another wild card is the stability of protons, the building blocks of atoms. In our everyday life, protons are effectively eternal. Yet certain grand unified theories predict that protons can decay perhaps on the order of 1.0 circumflex 3-4 years or more. Experiments haven't seen this decay yet, so if it happens, it's even slower. But if protons do decay, then even atomic nuclei will disintegrate. After every star is dead, after black dwarfs or white dwarfs have faded, protons might still be decaying quietly. Eventually, even these fundamental particles could turn into lighter particles, positrons, neutrinos, photons. The universe would be stripped down to a thin fog of radiation and elementary bits. It's a speculative twist, but one favored in some physics models. Meanwhile, the black holes remain. These heavyweights are the last reservoirs of coherence in the late universe. A stellar black hole, just a few times the sun's mass, actually takes an inconceivable 1.0 circumflex 6-7 years to evaporate through Hawking radiation. Supermassive black holes, millions or billions of times the sun, live even longer. Estimates range up to 1.0 circumflex 1.0 years or more. NASA puts it simply, black hole a few times. The sun's mass will outlive the current age of the universe by dozens of factors, and a galactic center black hole will endure far beyond that. Yet the inexorable physics is the same. Quantum effects at the event horizon steal away energy, and eventually every hole shrinks to nothing. In the far future, each black hole will end in a final burst of particles and radiation, a last whisper of information to the void. One by one they will fade, until none remain. Finally, the cosmos will enter heat death. This is the great thermodynamic finale. Everything at uniform temperature, nothing doing work, all processes at maximum entropy, after perhaps 1.0 circumflex 100 years or more. Every last structure will be erased. The cosmic microwave background, already just a few degrees above absolute zero today, will redshift to nearly zero, carrying a faint warmth from the Big Bang that becomes colder and more tenuous. Any remaining particles are spread so thin and uniform that temperature has become meaningless. The laws of thermodynamics tell us that once this state is reached, no energy flow is possible. No signals can propagate. In practical terms, the universe has become as dead as it can be, a virtually empty sea of cold radiation. In such a universe of uniform darkness and cold, what can we even call a signal? Physically, a signal is any pattern that carries information: a photon beam, a gravitational wave, a neutrino pulse. All of these require some change or gradient in the environment. But at heat death, there are no changes left, only monotony. Thus, the final signal must come before absolute equilibrium. That means it must arise from one of the last events, perhaps the final gravitation-driven flare from the last black hole evaporation, or the last neutrino flash from a collapsing remnant. After that, space is silent. The last message the universe sends might well be a proton's decay or a black hole's vanishing sigh. Hardly the kind of message we can easily interpret. For humanity, the practical last signal we could ever receive would happen even earlier. Remember that accelerating expansion isolates us. Eventually, only our local galaxies remain visible, so any signal from the wider cosmos stops reaching us. If dark energy keeps the same course, then perhaps in a couple 100 billion years, all external galaxies will be flying away faster than light, cut off from our sight forever. From then on, nothing coming from beyond our cluster can arrive here. In other words, the last cosmic signals we'll ever be able to catch would originate within our local group. Maybe a supernova in Andromeda, or a flash from the last dying star, or at best one of those hypothetical black dwarf supernovae before it vanishes from view. Anything beyond that horizon is locked away. Of course, by then humanity, and even its descendants, likely won't be around to hear anything. But if some astronomer were watching in that far future, she would know that after her last detected photon, the rest of the universe has gone forever silent. This is a deep, almost unfathomable vision, and it carries a heavy emotional weight. Why do we bother listening at all, knowing that the cosmos is so immense and our time so short? The answer is woven into our very nature. Looking at the stars has always been about longing for knowledge, for company, for understanding our place in the grand cosmic play. Each time our instruments fail to find a signal, we are confronted with silence, and silence begets questions. Are we alone? Is the universe empty of eyes like ours? Does it want to remain a mystery? The cosmic silence teaches humility. We realize that the answers we seek may not be written in the stars. Perhaps life is rare, or perhaps civilizations are so fleeting that they never overlap. Or maybe the universe simply has no one calling out. Each silent night sky is a reminder that even if the universe is indifferent to our hopes, our search was not in vain. It helped us learn about pulsars, about exoplanets, about cosmic dust, and the very physics of radiation. Astronomy advanced because of the search itself. We became a spacefaring, space-fishing species by listening, by probing, by dreaming. And in this quest, we shape ourselves. Projects like SETI, Voyager, or the Hubble telescope are as much about our self-image as about aliens. Launching a probe into the void, or encoding our messages on golden records, is an act of defiance against silence. It says, "We were here, and we listened." Each year we scan the skies with more sensitive ears, refining our place in the cosmos story. The blank space around us challenges us to improve, to collaborate across borders, to push knowledge further. Even without a reply, the act of listening has knit together generations of scientists, poets, and dreamers. Ultimately, maybe the last signal isn't a transmission at all, but the imprint of our curiosity. We might cast radio waves or lasers into space, sending a hello that could travel for millions of years. Those impulses could outlast our species, wandering the galaxy like cosmic messages in bottles. Our legacy might be in those photons or neutrinos we send out, faint traces of a civilization that once dared to reach out. In the deepest sense, every question we pose to the silence is itself a signal. By asking, "Are you there?" over and over, we tell the universe a story about ourselves, that we are alive, that we wonder, that we care. So we end where we began, in silence, but not despairingly so. The physics of the far future is cold and unyielding: expansion, entropy, decay. Yet the human narrative weaves meaning into that framework. As the last possible stars wink out and the final cosmic fireworks fade, our own inner light's curiosity, imagination, love of knowledge burn on. In the grand continuum of existence, our questions echo longer than we expect. The last signal, then, may not be a piece of cosmic mail we receive. It may be the enduring human spirit to ask, to know, to connect. In the quiet aftermath of everything, our story is what will remind the cosmos and ourselves that for a moment in time, we were listening. He last signal humanity may ever receive. Part 5, Epilogue. Silence does not arrive all at once. It creeps in, almost politely, as distances stretch and clock slow, as the universe gently forgets the shapes it once held. Long before the final star fades, long before the last black hole exhales its remaining warmth, there is a quieter ending already underway. The moment when nothing new can reach us anymore. From Earth or whatever world may one day inherit our curiosity, the sky will still glitter. Familiar constellations will remain, bound by gravity and memory. But beyond them, the wider universe will have slipped away, carried outward by the accelerating expansion of space. Galaxies that once painted the heavens will be gone, not destroyed, but unreachable. Their light will never again cross the widening gulf. For any observer left behind, it will be as if those galaxies never existed at all. In that era, astronomers may look up and conclude that the universe is small, static, and lonely. They may find no trace of the Big Bang, no cosmic microwave background, no evidence that the cosmos was ever young, or hot, or crowded with light. The signals that once told that story will have been stretched into oblivion. Knowledge itself becomes a victim of cosmic time. This is a sobering thought. It means that the universe does not only erase matter and energy, it erases information, erases history. And that brings us back to the idea of a last signal. A signal is more than energy traveling through space. It is meaning encoded into motion. It is the difference between noise and pattern, between randomness and intention. When we search the sky for signals, we are not merely hunting for aliens. We are searching for evidence that meaning can survive distance, time, and entropy. Every signal humanity has ever detected from space is already a message from the past. The light from distant stars began its journey before humans existed. Fast radio bursts reach us after traveling billions of years through ionized plasma and warped spacetime. Even the sun we see is not the sun as it is now, but as it was 8 minutes ago. Astronomy is archaeology performed at the speed of light. One day, there will be no more layers left to peel back. The final detectable signal, whatever form it takes, will mark the last moment when the universe still had something new to say. After that, everything that can be known will already be known, at least in principle. The future will contain no surprises, only gradual fading. But here is the quiet truth, hidden beneath the vastness of cosmic time. We are living extraordinarily early. We exist during a brief, luminous window when stars still shine brightly, when galaxies are still visible, when information still flows freely across the cosmos. We live at a time when the universe is loud with structure, variation, and possibility. The silence we fear is not now. Now, the universe is speaking constantly, in photons, in particles, in gravitational waves rippling through space-time itself. The fact that we can listen at all is remarkable. When humanity built its first radio telescopes, we did not know what we would find. Pulsars were once dismissed as interference. Fast radio bursts were first cataloged as anomalies. Even today, most of what we detect arrives without explanation, demanding patience and humility. The universe does not reveal itself all at once. It whispers, and sometimes it stays quiet long enough to test our resolve. And yet, we keep listening. We listen because silence is not emptiness. Silence is context. It sharpens our questions. It forces us to refine our understanding of physics, of life, of ourselves. It reminds us that existence is not guaranteed companionship. Perhaps there are other civilizations, scattered thinly across cosmic history, their signals passing through space long before or long after we were capable of receiving them. Perhaps intelligence is rare, fragile, and brief. Or perhaps the universe is teeming with life that simply does not communicate the way we expect. Science does not yet know. What we do know is this: the search itself has meaning. Every antenna we raise toward the sky is an act of hope grounded in reason. Every algorithm that scans for patterns affirms our belief that the universe is, at some level, understandable. Even if the last signal humanity ever receives turns out to be nothing more than a dying star or an.